Okay. Giving you this is a previous exam from a previous year, and it contains a T table, a Q table, and just one line from the Z table, and then some formulae to figure out how to do means and standard deviations. There is a little bit of blurb about the standard deviations. And then this is a Z table. This is the full thing. After we've used a Z table for a while, we end up we tend to use the same columns. So we'll come back to it. And then a little bit from the chapter about how to propagate errors. Okay, we'll do question number one. Question number one is about detecting outliers. Okay, so we have a set of data and they're bunched. It appears to be a linear trend with a positive slope, but it's not perfect. It's not truly linear. These right here are off trend. Human eye or the computer will put a line of best fit through that with the least squares analysis. And what we want to know is that a homogeneous set? Does everything on this page pass? Is it trustable? Okay, because if I have a dot that's here, it's a bit separated from the others, but it's definitely on the trend. If I have one that's here, okay, that is separated from the others and enough off trend for us to question, would my line of best fit be better if I ignored it? And I've said already, at the fall symposium, a whole bunch of people used the same data in their graphs, and they went, these were the values of pH. pH would have been here on this scale. I can't remember what was on this scale, but at different places in the preserve. So they tested the water, and there was a cluster right here, and then there was one there. But these were all pHs of 7 to 8, and there was a pH of 4. And I went, pH of 4? And the authors just looked at me blankly. That should never have made it onto their graph. They didn't do this analysis. Okay, so what we're going to do is we're going to look at that dot and say, do I include it? These people should absolutely not have included that. The way that we do that is with the Q test. Where is it? Our textbook, remember, has replaced the Q test with a G test. The G test requires a little bit more work. We'll do both. I'm not quite ready to give up the Q test yet, because the Q test is simple. It's simple. The G test requires you to do a little bit more work before you get to an answer. And I think you should do the least amount of work. Period.
I agree.
So what a Q test does is it measures the gap between data points over the range. And we will check the value of Q that we have calculated against the value of Q that is tabulated. There is a Q table. In that little packet that I just gave you, there is a Q table in there, and we'll show you how to use that. And if the value of the Q calc is bigger than the value of Q table, then go ahead and reject the data. Okay. Grubs this one I like because this one is easy. There's also a G test. This is Grub's test. Apparently no apostrophe. Not possessive. And G is, you have to know the standard deviation in order to figure this out. What you do is you identify which of your data points. Data, I hope you're aware, is a plural. Datum is the singular.
Datum? How do you spell that?
D-A-T-U-M.
Oh.
So I'm going to write it down now that I've said it out loud. So this is a single point, datum. And we're going to subtract the mean from it and then divide by the standard deviation. So this one requires, this one makes you do more work. And there's a G table, and if G calc is bigger than the G from the table, then you reject the datum. So our text says they have removed this from this particular edition of the text. So we went back looking for it the other day, and they've said they've replaced it for this, which means this one has to be better. But it does require significantly more work. This one's quick and easy, and I'm not ready to give this one up yet. What this is going to do, ultimately, is lead us to something called a confidence interval. And the question is, if you do an operation repeatedly, at how much confidence, as a percentage, do you think that you will do it right? Bearing in mind that your answers are a population. So you have a number, and then you do a procedure. It gives you a number, and then it gives you another one, and then it gives you another one, and then another one. And somewhere they're all under the curve. They have to be under the curve. Okay. The only time that they would be outside is if you made an error. Right? If you spilled something, so your numbers no longer make sense. So we have a confidence interval, and okay. Some things can exist at a different level than other things. Not everything has to be perfect. Typically, we look for a confidence interval of about 95%. If we do something in lab, we know that there's going to be random errors, there's going to be human errors. If we do something in lab, that should be repeatable about 95% of the time. Okay, if it does, then we're probably okay with that. If every time I get on a plane to take a flight somewhere, they say our planes fly with a confidence of 95%. I'm not getting on that plane. Because getting the answer right 95% of the time means getting it wrong 5% of the time. And a 5% error could be deeply, deeply unsatisfactory. Okay. So, our confidence interval represents the mean of your data is found in 95% of your experiments. Okay. That seems reasonable. That the mean of your data is in the data set, 95% of your collections. Let's write it out. So the confidence level is this. We're going to ask a question. We're going to do lots and lots of replicate measurements. They're going to give us small variations on those absolute numbers, which will lead us to a mean. The mean turns out to be our answer. Plus or minus its uncertainty. And the uncertainty is the value that we read from the t-table times the standard deviation, all divided by the square root of the number of values. Okay. This is our mean value. This is the value from the t-table. We'll show you how to read the t-table shortly. This is an S, it's not a sigma yet. Sigmas, when you've got thousands of pieces of information, it can be a sigma, it can be a population standard deviation. When it's an S, it gets to be the sample standard deviation. And we can do that by hand, or you can do it by your calculator. And then this is the number of data points. And there's a difference between populations and samples. But when you're a sample, we use S, we still use X and X bar, and we use N, the lowercase, and we use the T value. And when I have a population, My S is now a sigma. My X is still a value of X, but my X bar is now a mu. It's the population mean. So that's the sample standard deviation and the sample mean when I have data points somewhere between like 8 and 200, 100. When I get into the hundreds, into the thousands, I can switch and go population. That's the population standard deviation, the population mean. And we go N, we go capital N for the number.
I can inquire, what are the X's that don't have the bar?
It's just the value. That's an individual value, and that's the mean of the value. And then this is the standard deviation. This is the number. And this is T, is a made up value that's from a table. And when we use a large sample, and we become a population, we stop reading from the T table, and we start reading into the Z table. So right now we have 4 tables. You have a Q table, a G table, a T table, and a Z table. There's also an F table. The F table has a really good application that I'm not 100% sure that we're going to see. When you've got 2 things and they're kind of overlapping, I think we're going to hit the F table.
So T and G tables are for samples? So T tables for a sample,
Yes.
the G table is for what?
G is, so Q and G are to detect outliers.
Okay.
And when we've found an outlier and rejected it, then that's going to change the number, our number N of data points. And remember, there's another thing, degrees of freedom. This is the thing that we actually read off the table. If and when we reject a data point, a datum, it changes the number of data points in our set. So we have to worry about that. Okay, let's do question number 1 from fall of 2021. It says, an automated pipette was set to dispense 1.250 milliliters of dilute acid. In replicate measurements, the pipette dispensed the following milliliter volumes. So the first one was perfect. The second one was perfect. The second one, plus or minus here at the third decimal, 0.004. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just making sure they've got them all right. Looking at the trend in the data set, which type of error scenario best describes the source of variation? The device is miscalibrated to a higher volume. There are air bubbles in the pipette. The solution was made too dilute. There are water droplets on the outside of the pipette. Explain your answer. Okay. So the actual value that it was supposed to dispense was 1.250. And it's an automated pipette. So we know that a pipette is one of those kind of things, right? This is an automated one. So it fits on top of a bottle. Here's the bottle. And there's a downspout, and then there's some kind of little handle thing here that you can turn or screw in order to set the volume that gets dispensed. And then you put your hand on top like a soap dispenser, and it pipettes out a volume. It's like a pump dispenser.
Do we have any of those in lab?
Not in chemistry. Biology might have some. Biology have the Gilson pipettes.
Oh, like the ones with.
Yeah, they have it's a handheld device that has a dial, you dial in the volume that you want, and then there's a piston,
I've done those.
and it has a little tip, and you.
Oh, that one.
Okay. All right, look at the numbers and tell me what you see.
Progressively decreasing.
If it deviates, and it always deviates because there's less.
Less. Never more. So there is an error, but the error is always less, never more. One of the answer choices was, there are water droplets on the outside. If this is your pipette, and I put in exactly whatever volume it's supposed to be, and I dispense it, and there's a water droplet on the outside, and they make it into my container, into my Erlenmeyer or my beaker, then my value is higher than it's supposed to be. So it's not that one, it's not that.
Is it the air bubble?
I think it's air bubbles.
Yeah, so if there's an air bubble in the tube, then that's occupying space. It's occupying volume, but not dispensing the volume, because it's not really there. It's null. So that's my answer. Can any of the data points be discarded as outliers? And it says specifically at a 95%. You know, I put all of those on the board, and the camera can't see it. Yeah. It's a good thing I just double checked. There you go. You can see the top of the board now. Here's what we're going to do. So the question, part B, says, are we going to discard any of these? Maybe. What you should do is rewrite them in order, in sequence, from big to large. No, that makes no sense. From large to small, or from small to large. It's statistics. There's a certain amount of grind involved.
Is a lot of quantitative gonna be statistics?
No. No. That one and that one. And that one. And then this one. And that one. And then this one. And then that one. And then two of those. And then 1.236. And then 1.228. And then 1.108. That should give me 12 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. N equals 12. Okay. Q test. We're going to put gap over range. Which part don't you trust?
I don't trust 1.1.
That right there. That seems questionable. So the gap is the gap between it and its nearest neighbor. The range is the gap between it and the end. That's not right. That's 0.012. Was it 0.12? Okay. And 0.142. So this gives me a value of 0.845. This is my calculated value of Q. All right, let's go look at the Q table. You have a packet, and somewhere there is a Q table. table. I might have to pull up a larger one.
Yeah, for the 10.
Because yours, that one goes to 10. Did I give you two values of a Q table? Did I give you two of them? Because the book's removed its Q table. Oh. F table, T table. All right. Let's take a quick look. I have to. Yeah. So we need it to go to 12. What we're going to do is we're going to look at a Q table. I'm going to pull one up on the internet. And it reads this way. The n is 1, 2, 3, blah, 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 blah. And then it reads at intervals. And intervals will be like 50%, 90%, 95%, 98%. And you find the number that we're looking for, 12, and then you match. We're going to find what the number is in that box at the 95% confidence level. It says in the book, in the question. Look for the 95%. Now, when I first got introduced to this, I was like, I just don't like the wording here. This test, this is a Dixon's Q test, and what we'll do later is a T test, and the T test is called student's T test. Why are you not doing it? So I need a Dixon's Q table.
Are there multiple types of Q tables? Like,
No, they're all the same. They just go to different values. So here's one. We're going to open this. No. No. Come on. That's the one that I've been using. And it goes to 10. Okay. This is the Dixon outlier test. So I'll print this and give you this. Here we've got across the top 70%, 80%, 90. Oh, you can't see it. Make this be bigger. This is a big table. What we want to do is make sure that its numbers and our numbers are in agreement. They are not. I have not foreseen this. We need a T table that is bigger. There you go. How about this? It's from an actual text. What am I looking at? 10. 10. It only goes to 10. this one will work. I got one right here. Open image in a new tab. Oh, it's downloading it instead. Okay. This is a T table, Q table that we can. Oh. Come on. I've lost my mouse.
It's on the, it's extended. It was over there. Oh yeah, it's on the scene.
Where is it?
It's on that screen now.
I cannot get it to be over here. Does it go the other way? There it is. I'm gonna have to settings, display, extend, duplicate.
Yay, let's see it.
Okay. This is a Q table. And we're going to look in this column, the 95% confidence limit, and we're going to go to 12. And the value at 12 is 0.426. Confidence limits. There you go, that number, 0.426. 0.426. So, QCalc. Q table 0.845 is larger than 0.426. Therefore, you reject that data point. Don't include it in your set.
Sorry to interrupt.
Mm-hmm.
Do you happen to know where Dr. W is, or if he's gonna be here?
I don't know what time his class is. Is it at 1? I don't know what time he's going to.
Okay, sorry. Thank you.
Okay, so we're throwing that one away. The other things that you can do are, you can look at the gap up here and do the test at this end, and we're not going to throw that one away. Or you can go, well, do I want to throw this one away as well? You can go check that one, but we're probably okay. All right, so we're rejecting that data point. N now went down to 11. Okay. Next, calculate the mean and the margin of error for this piece of apparatus. The mean is the sum of all the values of x divided by the number of measurements. Now you have two ways of doing this. You can just type the numbers in. This plus 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 this divided by 11. Or you can go to the stats page on your calculator You both have the same calculator, but it's not.
Do you have K 4 plus?
Yes.
I don't know how to use those.
Do you know how to use this?
Wait.
You go to the stats package and you input these as data points, and then it will find the mean for you. There needs to be a separate 15-minute tutorial.
We'll just go look it up on the interwebs.
Yeah.
That's what happens. So okay, so it's that. Okay, on the L1.
Oh, no.
Okay, great.
Or you can just do it by hand.
Honestly, I would probably be more comfortable with.
Me too, but I didn't learn how to use this again.
So if you go to the statistics part of your calculator, it lets you enter. You put the number in and press enter, I guess, and you keep entering them, and it will tell you n equals 11, x bar is this number, and s is this.
I can do a Z-test almost.
Yeah, that's what I tried to, but I didn't put still so much harder than it needs to be. Swear it used to be easy. Ooh. Me.
Wait, how did you get me?
Yay! Okay, so we go to stats. Well, actually, no. So you go to second stat.
Oh, list.
Yeah, math, then me. and
Say
then
that
you
out
go
loud.
L1. So you go to second stat, which is really list. And then you go to math.
Right twice. Yeah. Okay. And
Oh,
then,
yeah, to math. That's what she means by right twice.
Yeah.
So you go to math. And then on math, you click on 3.
when you scroll down to 3, yeah.
Which is mean. And then when you click on that, you have to input your list. So you already had to have it in a list, but if you put it in list 1, then you put L1.
I don't know what that means.
So at math and then me. So then we had to go to second L1 because I already put the list in L1. So I went to stat, edit.
How'd you get the numbers in the list?
I just typed them.
Just typed them in.
all into
L1.
L1.
Okay.
I don't know how to explain it.
Mm-hmm. Okay.
You just input your.
All right. So,
numbers and scroll down.
this is our mean.
I got 1.2 from 2.
Yeah, your calculator says 2.
Well, it has a whole bunch of
I have
numbers where-
rounded that number up. What's after the 2?
a 7. So.
Mm.
Okay. Wait. Why are you looking at
It's a 3. Okay. Now,
That's
that's a number, but it comes, this is a milliliters. Because this is a volume, and it comes with an uncertainty.
No, that has nothing to do with anything.
I'm sorry, I don't know.
We're good.
We'll
I'll figure this
figure it
out
out.
later.
Hers rounds it already.
My round, so mine left it as like a float number, like it floated instead of rounding it up. That's it.
We have a number, it's given
Okay,
us an
that's-
answer, that this pipetta is dispensing 1.243 milliliters each time, as an average, as the mean. But we have an uncertainty that we haven't met yet. And that uncertainty is TS over root of n. So we need two things. First, you've put your numbers in a list. It's there, x minus x bar squared over n to get to the standard deviation, or let your calculator do it, because it already has it. Standard deviation is the root of all of the gaps between the actual values and the mean of the values squared, all of them, the sum of all of them squared, divided by
Is it
the
7 on math?
n, but not
So if I go
counting
second
yourself.
stat, so I get to list.
Oh, and
Right,
then you went over to
math, and then
Yeah, I did 7.
Okay, I got it.
Okay.
0.007. One, how many are you rounding to?
Three
Well, one
seems to
five.
be
0.5.
okay. Now, are we sure we got that number right? Because at this point, are we confident that we're doing this correctly?
I'm not.
No, I mean, because the calculator tells you things sometimes, and you have to take a step back and say, wait a minute, do I believe you?
Wait, did you get 711 or 706?
I got 0.0071146.
Okay. I trust yours more than mine though.
It should be the same number.
This should be, we don't know what's going on.
Mine's weird. I'll figure that out later.
Okay. Leap of faith of, is this number meaningful to me as the standard deviation? Well, it turns out the standard deviation should be kicking in right about then, at the third decimal. So although I don't know what voodoo the calculator did in order to get that number, it's given me a number that looks like a standard deviation, because standard deviations kick in at the least of the significant figures. So there you go. All right, that's the S. Plus or minus TS over the root of n. All right, T. Now we need to look at a T table. Here's a T table. The T table. It gives us confidence intervals across the top, and it gives us degrees of freedom in this column. All right, a couple of things to know. N equals 11. Our number of data points is 11. That means that the degrees of freedom n minus 1 is 10. So I need to look at this table and not read down to 11, but read down to 10, because I'm going to read degrees of freedom off there. Across the top, we don't have percentages. What we've got here is the error as a value, okay? So the first one is 0.4, which means 60% of it is correct, 40% of it is incorrect. These are usually written as percentages. So what we're looking for is the one that says 0.05. That represents 95% correct, 5% not. So 5 divided by 100 is 0.05. That's my error. This is listed, this is cross-listed as an error instead of confidence. Okay, so we're going to go find that column right there down to 11, and whatever number is in here, that's the number we're going to use.
I'm a little confused because at the bottom they have percentages and the 95
Oh, it does.
is under the
Oh, well, there you go.
0.025.
Okay. Confidence limit's actually at the bottom. Overruled what I just said. Confidence interval is at the bottom. So from your 95% column, read up. We have 11 data points. We're going to read until we get 10 degrees of freedom. And that gives you a value that is
2.2281.
yes. Yes. So from the t-table, using n equals 10, and the confidence interval is 95%, it says that t is 2.22814. Okay. All right.
So what is it? T? Why do we need T?
It's the it kind of measures what's in and what's out. So we're gonna look at, there's your mean. I'm gonna look at this particular part right here and just know what's in and what's out. That's not a particularly good explanation, but it'll do.
So that's is that like the 5% that they split in half for each of the two sides?
Yeah, if it's, yeah, because it can be one-sided or it can be bilateral, yes. Okay, so I have that value of t, I have this value of s. So let's put all of this together. That the volume dispensed is the mean plus or minus t, standard deviation, divided by the root of the number of points. So this got to be 1.243 plus or minus 2.2814 times 0.00711, all divided by the root of 11.
for the plus or minus fraction, I got 0.00478. 478, but going around something, I don't know how much.
So 478, how much of that is trustable? I can't really have precision out to here because that's more than I'm able to measure. So I would go ahead and round that up all the way up to a 5.
Okay.
Because at this point you're inventing precision. And yeah, that's a bit of a leap, right? But the final number came out to be at the 3rd decimal. Sigh of relief. Because if it wasn't, we would probably have to go back and find where we made the calculator error. Yeah. Your deviation, your uncertainty is happening here. Okay. All right. There's a couple of other things. Let's see what else we've got. How about relative standard deviation? Excuse me. I got that written down somewhere. Oh, we never did do the G test. You want to do, so now that you have S, so you can't do the G test until you've got S. Whereas you can do the Q test straight away. So I kind of like the Q test better. But if you wanted to do the G test, let's do it once and then figure that. Then I can say we've done it. What number did we discard?
1.108.
Okay. All right. Let's do the G test. The G test is what? The value. It's the thing that we're questioning. And we're going to subtract from it the mean. Yeah. And then divide it by S. So we had to do much more work.
So we would have, so for the mean and S, we would have to include the questionable data too? Like, because we calculated the
Yeah.
deviation and the mean without that data.
Yeah. Oh, I'm not doing this again. You want to do it again?
No, I'll do it later. No.
Yeah.
It's okay.
Yeah. So this would be a different mean and a different.
I could do it real quick.
Yeah.
Okay, I'll also.
We know what's going to happen. It's going to tell us to reject it. Yeah, it'd be a different data set. Okay.
So for the G test, you don't have to look for an outlier. Is that what you're saying?
The G test does look for an outlier. It uses a G table, not a Q table. And if the calculated value for G is larger than the value from the table, then you reject the number.
Oh, okay, so
It's
there's
exactly the same process, only the math is more difficult.
Okay.
And when you're done with it, you throw away
Both of those data.
15 minutes, how many minutes of work?
Probably 5.
You're going to throw away the amount of time that you did this. It's like when we do ice boxes in equilibrium, and what the textbook says is if you want to know whether you can use an approximation for rounding, do the quadratic, do the long solution, and then throw your numbers back into the question and see, did they have an impact? No, that's too much work. And when they don't have an impact, then you use the approximation and do your math again without it. It's too much work.
This is not it.
What number did you get at the end?
1.2315. For the mean. Oh, I'm sorry.
Oh, you're good, I'm already got it, yeah, I already got it, yeah, 1.2315, yeah. And then for.
I don't know about this being a negative number, or if it's just a.
I keep getting positive stuff.
Oh.
But, so, for whenever we look at the G table and the what's it called? Degrees of freedom, do we use 11 then?
Yes.
Or do we, okay.
Yes.
You're getting a positive number?
I got a positive number.
Well, oh, yeah, surely this number is smaller than the mean,
Oh.
so that would be a negative number. I think he
Oh,
just.
I added it, that's what, or I multiplied it. Oh, yeah, I definitely.
Someone might ask you, what is the relative standard deviation? And the relative standard deviation is the standard deviation divided by the mean. And those numbers are all off the board, so I have no idea what they actually were.
Dr. Barr, what's the purpose of the relative statement?
That's a really good question.
I make statistics.
Did I get one there?
Oh, I love her, she's the best.
She is the
I had her for life and leadership last semester.
You got to have her?
Yes. She was the best, I loved her.
I
Our
love
class
her.
was so quiet though, I felt bad, so it was like.
So
one of the kids
relative
actually
standard
was
deviation is a
crying.
special form of the standard deviation. You may want to read this article first. Is generally reported to two decimal places, the RSD. The RSD tells you whether the regular standard deviation is a small or large quantity when compared to the mean of the data set. So we can it's gonna kind of set itself up to be converted into a percentage. The relative standard deviation tells you whether the regular standard deviation is a small or large quantity when compared to the mean of the data set. For example, you might find in an experiment the standard deviation is 0.1. If your mean is 4.4, then your RSD for this data set is 2.5%. This tells you that the standard deviation is 2.3% of the mean, which is pretty small. In other words, the data is clustered around the mean. On the other hand, if your percentage was very large, say 55%, then it would indicate that your data is more spread. So the relative standard deviation
That makes sense.
is usually written with the mean and a plus or minus symbol. It's often written as a percentage. Okay. There is a bit more. Let's look at a previous exam question and then we can give up. There's a previous exam question that says, here's some numbers, find the mean, find the standard deviation, find the relative standard deviation, find the confidence interval. Then, this particular analysis has been performed so many times that there is an established population for this data. That means that there is a population standard deviation. It's not a sample anymore. It's now a sigma. It's not an S. It goes up to being a sigma. Calculate the new confidence interval for mu, your mean, population mean, at the 90 or 95% confidence interval. What we would do is we would go to a Z table. So, confidence interval. For a sample is the mean plus or minus the value from the t-table multiplied by the standard deviation, all divided by the root of n. If we're doing this on a bigger scale for a population, then mu is now our mean plus or minus z, not t. T-tables are for samples that have handfuls of data points up to a couple of hundred. Z-tables are from hundreds into thousands of data points. Sigma over the root of, actually, that gets to be a capital now. Okay. And somewhere in that packet that I gave you, we do have a big, I think I gave you a big Z table, but then occasionally all we ever need is the one line that says, if you've got so-and-so. You don't usually need all the data from the Z table. Okay, all right. Thursday. We'll do our first chemical topic. We will revisit equilibrium, and every time we said in chemistry 2, this could go wrong, but there's an approximation that we're just going to let it be. We're going to have to retract all of those approximations. Go with the real values.